We're going to go through the Year 8 key assessment of the atmosphere and oxidation reactions in this video. Please make sure you fill in your corrections as you go through the answers, and make sure you do pause, and if you have any questions, please do ask your teacher. Okay, so we have a list of gases. The questions asked us to underline the gases that are elements. Now, elements are all found in the periodic table. So you should have underlined argon, hydrogen, nitrogen, oxygen, and chlorine. If you can't find something in the periodic table, then it's not an element. Part B asks you to draw a box around the gases that are compounds. You should have had water vapor, carbon dioxide, and sulfur dioxide. And these aren't elements, and they can't be found in the periodic table. They're compounds because they contain two or more elements that are chemically combined. So in water vapor, that's H2O, so that's hydrogen and oxygen. In carbon dioxide, it's carbon and oxygen, and sulfur dioxide, it's sulfur and oxygen that are chemically combined. Now you would have got 1 mark for that. I think it might be helpful to go over the definition of what a mixture is then. Even though you wouldn't get a mark for it, but a mixture is two or more substances, and a substance, I've put the definition of a substance above, and a substance contains only one element or compound and is pure. So a substance is an element or a compound essentially. So H2O, pure H2O is a substance, pure magnesium is a substance, but salt water isn't a substance because it has water and salt in it. So it has to be pure to be a substance. So a mixture is two or more substances, not chemically combined. So you can separate it quite easily using filtration or some other technique like evaporation, distillation or something. So these are your percentages of each of the following gases in dry air. These questions normally do specify dry air because normal air would have water vapor in it, and that changes with humidity. So in perhaps a rainforest, you may have a higher percentage of water vapor than here in London. So a student used this experiment to calculate the amount of oxygen in air. He used an inverted measuring cylinder, filled it up with oxygen, and put damp iron filings at the top here, and left it for 2 days for this reaction, the rusting reaction, to happen, and your iron and water react with your oxygen in the air to form hydrated iron oxide, which is rust, which is the orange stuff that you may see on your bike parts, and your oxygen turns from a gas to a solid, so it takes up much less space. Just to give you an idea, thousands of times less space than what the gas takes up. So therefore your water level rises and tells us how much oxygen has been removed. In this reaction, you want to ensure that you have enough iron and water to react with all of the oxygen in the jar. If you don't, in this measuring cylinder, if you don't have excess iron, then not all of the oxygen will react, and your water level won't move up as much, and the value that you get for oxygen is going to be lower. And that's also the same as if you don't leave this reaction to happen, this reaction to go to completion, then again all of your oxygen won't have reacted and you'll get a lower result or percentage. So calculating the percentage of oxygen in the air, what we need to do is we need to calculate how much oxygen has been removed and then put that as a fraction over the total amount of air we started with. So 15 centimeters cubed of oxygen was calculated, and we've got to divide that by the total number of air we had at the start and times it by 100 to make it percentage. Now, these brackets and ones here just tell us that we get 1 mark for each. I would always recommend putting your having your calculations in, just so we can see where you went wrong, and we can see that and you can see that and learn from it. So this is not as high as we would expect it, and these are 2 possible reasons. So you get 1 mark for saying that the value is lower than what we expected. and these are your two reasons. We could improve it by leaving it for longer or using an excess of iron filings, and both of these reasons is to ensure that all the oxygen has reacted. So these are all the word equations for the oxidation reactions of each of these elements. And just be careful that when they all form your metal or non-metal oxides, but you do need to remember that nitrogen, sulfur, and carbon all form dioxides. So your sulfur and carbon form dioxides instead of just oxides. Question 4b, your oxidation reactions when substances gain oxygen or when a substance gains oxygen. A practical test you can carry out to see whether the product is an acid or alkali is you could add water and then universal indicator solution or paper. You'll get 1 mark for saying water and then 1 mark for saying either universal indicator solution or paper. It doesn't matter which one. Universal indicator solution and paper, as you know, are quite special. They tell us the pH as well as whether it's acidic or alkaline. I would say stick to these two, even though the question will allow the use of other indicators, but these two specifically can just give you a better idea. As per the videos you've watched, they're better. So part C part 2, it says state which of the products from burning the elements above are acidic and which are alkaline. You should know that your metal oxides are alkaline and your non-metal oxides are acidic when aqueous, of course. And aqueous just means dissolved in water. If you can remember the state symbol for aqueous, it is another separate state to solid, liquid or gas. That's because when you dissolve things in water, they do have different properties. And the state symbol for aqueous is AQ.